So here we have a three-phase brushless DC motor which actually consists of 12 stator poles. Now this is still a three-phase motor, but those three phases are split among 12 stator poles. And here's how it's wound. Let's say, for example, that we have a coil coming in here, a wire coming in for phase A, and it's wound in such a direction that positive current will create a south pole in the air gap right at that point. And then the wire jumps over here to phase A bar. It's actually wound in the other direction around that stator pole, so that the same positive current now creates a north pole in the air gap there. After that, then the wire loops over here again to phase A, where it's wound in the original direction, and then once again over here to phase A bar, where it's wound in the opposite direction, and then it connects to the center node inside the motor. And that's the same way it is for all three phases of the machine. So we can actually see here that we have, for these 6 diagrams, these are the 6 stator commutation states, which are determined by detecting where the rotor is, and then once we know where the rotor position is, we know which commutation state that we should apply. So let's take the example of diagram number 1. The rotor is in this position right here. We have actually sensed it with the Hall effect sensors, and from that information, assuming that we want positive torque, we know exactly which stator phases we need to turn on, and in this case it's phase A and also phase C. And what you'll notice is that with phase A and phase C, that creates this magnetic pattern on the stator, and all of the stator magnets are working together in conjunction with the rotor magnets so that they're all producing clockwise torque. Can you see that? So the motor starts to move, and this south pole right here, for example, starts to move toward its happy state, and that happy state would be when this south pole is under both of these north poles right here of the stator. But before it can get there, I detect with my Hall effect sensors that we've crossed into another commutation zone, and that commutation information tells me to turn off phase A and now turn on phase B. So if you look at the magnetic pattern on the stator that is created when I do that, it effectively advances my magnetic pattern on the stator by 30 degrees. That means that the rotor has even farther to try to get to its happy state, and as it starts to close in on the new happy state, once again I cross another commutation zone, and the process continues on and on and on. So it's kind of like the donkey and the carrot. You know, you have a donkey and you have a stick on its head with a little carrot dangling out in front of its face. And of course, as the donkey tries to get to the carrot keeps getting further and further out ahead of him. And you know, I realize that this is a very cruel trick to have to do to my motor, but it's the only way that I know of to try to get it to produce torque. I don't want it to just sit there and not do anything. So that's how the commutation process works. Now you'll also notice that after it's commutated through all 6 commutation intervals, in this particular case, if you follow the dot on the rotor as it's spinning, 360 electrical degrees has only resulted in 180 mechanical degrees. And the reason for that is on this particular motor, it's a 4-pole magnet on the rotor. And that's the relationship. You take the number of poles on your rotor, divide by 2, and that becomes the multiplication factor between electrical degrees and mechanical degrees. Here's a picture of a rather interesting motor which I have in my lab, and you can see it's a 3-phase machine, but it does consist of 12 stator poles, just like we talked about in the previous slide, and it's a 4-pole rotor. You can actually see some of them here, some of the division between 2 of the rotor pole pieces right here. So this is just like the topology that we talked about in the previous slide, with one exception, and that is this is a cup design, so the rotor is actually spinning on the outside of the stator pole pieces. Now there's several reasons why you might want to do this. One advantage with this topology is that as the motor goes faster and faster, you don't have to worry about the magnets flying off the rotor and expanding into your air gap. In this case, what it does, if anything, is it actually makes your air gap a little bit bigger as the rotor pieces by centrifugal force are pressed against the outside of this shell here. Now you may notice this little starburst pattern right here around the circumference of the motor. And in my seminars that often comes up. People ask, what is that little starburst pattern? Very, very interesting. Well, it turns out that this disc right here, this magnetic strip, which is on the face of the rotor, it also consists of magnetic partitions of north-south poles. And as the motor is spinning, it actually will create, those magnets will create a little back EMF signal in this winding, if you will, and that can be amplified to give you good speed information when the motor is going relatively slow. Now, you can get speed information off of the Hall effect transitions as well, but the problem is, of course, when the motor starts going very, very slow, those transitions are few and far between, and as a result of that, you can use something like this to actually get much better speed resolution with your motor. So anyway, I just wanted to show you this picture. This is a rather interesting motor and a typical example of a brushless DC motor construction. Returning to our controller diagram, we see that the Hall effect sensors play a pivotal role in the control of a brushless DC motor. In fact, without knowing position information of the rotor, it's impossible to know how to commutate the machine. But the problem is that the Hall effect sensors in themselves are very expensive. You have to have some kind of magnetic disc that the Hall effect sensors are sensing. There's lots of wiring associated with it, especially if your controller and your motor are separated by any appreciable distance. Then all of that wiring and harnessing represents a significant part of the cost. And then you throw in the reliability problems of, bad connectors. What happens if a connector shakes loose or something? The additional power supply that's required in many cases just to power the Hall effect sensors. So there's lots of reasons from a safety point of view and from an economics point of view why you would like to get rid of those Hall effect sensors. But is there another way that we can get rotor shaft position information without having the Hall effect sensors? And it turns out that there are ways you can do that, and one of them is based upon back EMF sensing. In other words, remember, we've always got one coil with the way we've talked about driving it so far. We've got one coil that is unenergized, and we can actually snoop on that coil and listen to the back EMF signature, and from that we can get information about where the rotor is. And there's lots of different ways to do it, but most of them are based upon detecting the zero crossing of the back EMF signal.